So here's another problem involving Faraday's law. Induced voltage is equal to negative N rate of change of magnetic flux. So that means induced voltage is negative N times ddt of the dot product of magnetic field and area, which means it's negative N ddt of B times A times cosine theta. So one option for inducing voltage is if there's some value of dB dt. The second option is if there's some rate of change of area, or a third option for inducing voltage is if there's some rate of change of the angle. So here's a problem with a slide wire generator. And in the slide wire generator, the magnetic field is going to stay of the same value. In this problem, let's see, are we given the strength of the magnetic field? No, that's what we're asked for in this case. What value of uniform magnetic field would induce a current of 1 milliamp? But the idea is whatever that uniform magnetic field is, that it is uniform. There's the key word. So this is a problem which there is no rate of change of magnetic field, and the angle looks like it's equal to 0 degrees. If we picture this as the area, then the normal vector to that area points along the same axis as the magnetic field. Here all the x's are telling us magnetic field points into the page, and the area vector also points into the page. So there's no d theta dt. So this is a problem where we have induced voltage because of a rate of change of area. So in that case, and this is also a case where n equals 1, there's just one loop. So the magnitude of our induced voltage is equal to, let's see, cosine of 0 is also going to give us 1. So we just need to look at n times ddt of BA, but the B is constant and the n equals 1. So this is just a case where the induced voltage is equal to B times dA dt. So let's give some labels here and call the length of the rod L, and then that's one of the sides of our area, and then the other side we'll call that the width, and we'll say the width is a measurement along the x-axis. So as the rod slides to the right, then W is going to become greater. So L stays the same, but the width is changing. Okay, so we can say our EMF is equal to B times the rate of change of the product of length times width. But if the length is constant, then we can say the EMF is BL times the rate of change of the width, which would be the same thing as dx dt, which is the same thing as the velocity with which the rod is moving. So there you have it. The induced voltage is BLV, and we're asked to solve for the value of B. So B is equal to the EMF over the length of the rod multiplied by velocity. Let me see how many of those values are given. The velocity is given as 20 meters per second. The length of the rod is given as 30 centimeters. Oh, and we're not told the EMF, we're told we have a current of 1 milliamp going through an 8 ohm resistor. So by Ohm's law, V equals IR. So if you multiply 1 milliamp times 8 ohms, you get the induced voltage. So 1 milliamp is 0.001 amp. The resistance is given as 8 ohms. The length is 30 centimeters, 0.3 meter, and the velocity is 20 meters per second. Grab a calculator, let's see what we get. and I got a value of 0.0013 Tesla.